Hi, everyone. We're just going to wait one more minute for more attendees to join the session, and then we will get started. All right, before I get started, Andrea, I hope you can hear me and see the slides as well.
Yes.
Okay, thank you so much. All right, let's begin this webinar. Hi, everyone. I'm Sidesh here, excited to welcome you to our webinar on AI for reliable and resource-efficient industry. Before I welcome our speaker today, I wanted to give you an introduction to this webinar on basic housekeeping rules, introduction to the project, and also a little bit information about our speaker as well. At first, I would like to also share a little bit information about EIT Digital. EIT Digital is an impact organization, which is Europe's largest innovation ecosystem. We connect companies, startups, universities, and research centers from across the continent, and our mission is to grow Europe's digital excellency to accelerate innovation and support research while nurturing the startup system. This session is made possible thanks to the European Commission's funding of an innovative project called SME for DD. SME for DD stands for Training SMEs for the Digital Decade in three areas of artificial intelligence, blockchain, and cybersecurity. In today's webinar, I would like to introduce you to Professor Enrico Zio. Enrico Zio is a full professor at the Center for Research on Risk and Crisis of École de Mines, Paris Tech, and at the Politecnico of Milan. He serves on the board of the Fondazione Politecnico di Milano and is a distinguished lecturer for the IEE and Sigma SXI. In 2020, he received the prestigious Humboldt Research Award from the Alexander von Humboldt Foundation in Germany. He's a pioneer in his field. Professor Zio has made fundamental contributions to the development of advanced Monte Carlo simulation methods, dynamic risk assessment frameworks, artificial intelligence techniques, and evolutionary optimization methods applied to the assessment of risk and resilience in complex engineering systems. He's also the author of the paper and MIT Technology Review article, Artificial Intelligence Industry 5.0, Competitiveness, Opportunities, and Risks. We're very excited to welcome you, Professor, with us. Before I pass on the floor to Professor Enrico Zio, a couple of workshop protocols. We request you to keep your microphones muted to maintain focus and avoid disruptions. You can use the chat box in Zoom to, let's say, post your questions, which can be addressed by our speaker. The session is being recorded and it'll be used for internal purpose only. As I mentioned that today's session is made possible thanks to the European Commission's funding of a project called SME for DD. The project SME for DD is delivering short-term training programs in three strategic digital technologies for Europe, which are artificial intelligence, blockchain, and cybersecurity. These programs are tailored for SME leader professionals, combining strategic perspectives with hands-on applications. We are led by a consortium of 7 partners, of which EIT Digital is the lead coordinator, with training providers like Inria from France, Hyper Island from Sweden, BME from Hungary. We are also lucky to have networking organizations like Asintel from Italy, Talent and DKF from Hungary as well, who are also helping us on the project. And also a mention to Talent Garden from Italy, who's also supporting us on the training in this project. These multilingual courses are being delivered over the course of these 3 years in France, Sweden, Hungary, and Italy in French, English, Italian, and Hungarian. The different list of courses are available on the website over here. I will drop in the link of the website course. You can also consult our portfolio to know more about our work being done and also the different courses and workshops that will be available for the future. Without much delay, I would now like to pass on the floor to Professor Enrico Zio. So the stage is yours.
Thank you very much. Thank you, and thank you, Dr. Farulo, for the opportunity of sharing with you some reflections and some experience on the use of artificial intelligence, in particular for industry, of course, and for the key indicators or key objectives of being reliable and resource efficient. Who wouldn't want his or her industry to be reliable and resource efficient? So I got a very short agenda with hopefully sufficient time for a discussion. After a small framing of the context of the presentation, I will focus on AI in particular within reliability and even more so maintenance engineering. And then for the resource efficient part, I will look into the energy savings that we can have thanks to AI and how we treat AI, how we treat data with AI. Then finally, we close with some trends, opportunities, and challenges, okay, because the use of AI in industry brings also some challenges that we should be aware of and that we can together, of course, overcome for the best use of AI in industry. Now, let me start then. Of course, you know better than me what do we want from a reliable industry. In the end, we want to trust it to deliver what we expect in terms of product and services at the high level of quality that we need and we expect. Of course, we want the products to function as designed, as intended. We want the services to be delivered with stable and predictable operations. And of course, our clients and all stakeholders involved want to be able to count on the industry for meeting their needs on one side and their expectations on the other side. Now, these, of course, want to be done in a durable way, so not just at certain times or not just for a few months or years, but the effectiveness of the production of the industry needs to be for a significant period of time. Of course, there are constraints, there are regulations, there are standards that need to be guaranteed in terms of safety, quality, and ethical practices. And of course, things can happen that can disturb the production, can disturb the quality of the products. And so we want an industry that is also resilient and recovers promptly from any particular disruption that may occur. When we look into resource efficient industry, this is clear. There's a more and more stress, tension, and pressure of doing our productions with less or the just amount of resources. This entails, requires a life cycle thinking in order to minimize the environmental impact and minimize the use of resources. And this needs to be done and start from the design point, from the design task, with designing products which in fact are sustainable in all senses. And the process also needs to be designed and operated in an optimal way in terms of being resource efficient. Finally, of course, all the things that need to be put in place for minimizing waste and losses. So this is a very trivial contextualization of what is desirable for an industry in terms of reliability and resource efficiency. And where does and why can AI be an interesting element in support of the reliability of the industry, in support of the efficient use of resources? Well, AI comes into play because it does tasks that are typically associated with human intelligence and that we use and do these tasks in the design, operation, and management of our industry. Tasks like learning from knowledge and data, tests of drawing conclusions, solving problems, making inferences, being able to interpret information collected by sensors, images, text, signals, being able to assist in the decision making for optimal policies, for example, maintenance policies, and even being able to create content like music, sound, text, and data. And this is the big hype on generative AI in various application fields, not only on industry. So the fact that artificial intelligence enables these tasks that are typical of humans are very interesting for industry that is, of course, designed, maintained, and operated by humans. And the underlying big advantage is being able to do these tasks on massive information, massive data, which really can help disentangling the understanding of what's going on and taking the right decision in an optimal way. So for the reliable desire of our industry, I will look in particular in reliability and maintenance engineering, even more in maintenance engineering. And for the resource efficient desiderata or desire, I am going to show you some examples of energy saving. Okay, so let's go into reliability and maintenance engineering. Of course, reliability, we are expecting our system to provide the function that it has been designed for under the conditions that we have foreseen of operation and for the design period of time. And that's why at the design level, okay, we optimize the configuration of the components that must together provide the system function so that they are more robust, more reliable. We don't put the elements in series so that if anyone fails, the overall system fails, but we put them in some configurations of parallel systems so that if one of the components fail, the system can still work. And this is at the design level. When we operate the system, we still want the system to operate and provide its function. And therefore, we need to manage optimally the maintenance, which means to do at the right time, the right action or intervention of maintenance in the right way, including all the compromises with respect to the budget available and including the respect of any regulatory constraint and safety constraint. So if we open a little bit the maintenance aspect, okay, and we imagine then to exploit what AI can do, the fact that it can learn, the fact that it can make decisions, okay, we can think about some sort of knowledge feeding for reliability-centered decision making, okay? So of our system, for example, made by one component A in series with a parallel system that has component B and C, we usually look into how to respond to the question, what maintenance to do and when, based on the, let's say, black data, okay, failure data and expert knowledge. We collect some statistical data, and then we have the experts that tell us, okay, you should probably maintain component C every 6 months. Nowadays, there's a whole box of more and more knowledge and information that we can bring in about the components that can support our decision making for maintenance. We have physics-based models, mathematical models that describe how degradation, corrosion, fatigue evolves in time. We collect sensor signals, sensors data from vibration, temperatures, flows, that tells us how the process is going on in the component. We have images that are taken by, some types of thermographies, different types of, let's say, photographies, and so on. And then we have a lot of knowledge that is embedded in the many inspection reports and maintenance reports that have been collected throughout the life of the components when you go and check the status of the component. So this is a very interesting additional information that it would be very nice to be able to elaborate to help the operator decide what to maintain, when to maintain. So imagine, moving forward. Yeah, okay. So imagine a KID elaborator, a knowledge, information, and data elaborator, an artificial intelligence algorithm that is able to elaborate, manipulate all this information, and be able to direct decisions on, for example, telling us that there is something wrong in the component. So detection of anomalies in the production process, detections of degradation in the product performance. And then even more, it's able to elaborate, this elaborator, okay, it's able to elaborate what is known, what is collected as knowledge, information, and data, so as to tell us, look, it is component B that it is anomalous, and it's due to this particular degradation mode 1, corrosion, okay? And even more ambitiously, maybe being able to say, well, given that I detected that component B is having a degradation mode, okay, 1, I'm going to predict what is the time at which I expect the component to fail due to this degradation mode. And therefore, I know the remaining useful life, and I can plan opportunistically, based on this remaining useful life, the maintenance of the component before it fails, and not too early before it fails, because otherwise I would lose all the time of usage that I could have exploited. So I don't want to perform maintenance every 6 months if the component is expected to fail 5 years from now. Okay, so this is, if you think about it, and it's called prognostics and health management as a framework of analysis. It's very similar to the medicine, to the doctor, okay, of our component. Our component is the patient. We have some experience on this type of components because of failures in the past of similar components. We have the expert that is knowledgeable about the cure for this component, and we have a number of information, including medical texts and so on. Based on all this, the doctor tells us if there's something wrong, what is the illness, so the medicine that needs to be taken, and how much time we have before we run into some particular problems. So with an example, okay, let us take the effort for building an automatic diagnostic systems for trains, considering a large number of trains where we want these automatic diagnostic systems to work, okay? So now, the classical standard approach would be to, first of all, define by expert knowledge what are the failure modes that can occur in the train and need to be detected, okay? Then we need to do a mapping between the sensors data that we are collecting during train operation and the different failure modes that we want to recognize in order to be able to discriminate. Then we collect data from sensor from an experimental campaign and also on the field. And finally, we do our diagnostics by matching, building the algorithm that matches the recorded signals on the running train with the state of its components and its systems, with the detection of the failure mode. Now, the current weight approach for having an automatic diagnostic system, of course, has major limitations. It is not scalable in complex systems that are affected by many failure modes, because it's the experts that need to characterize quickly the anomaly and associate it to the signals that have been monitored and associated to the proper failure mode. And this could take too long and be too difficult. In fact, the diagnostic analysis is done by the experts, and the times for troubleshooting become very, very large, and you need to stop the train and leave it there until you know what's happening. Okay, and the difficulty here is there's a lot of signals that are collected. There are, a number of failure modes. How do I construct the map between the signals collected and the failure modes that I want to detect? So we tried to develop a automatic approach using artificial intelligence that exploits all the knowledge, information, data available, which in this case is the large amount of data collected by the sensors on the trains, and also the inspection reports, the maintenance reports, which are texts, but they can be transformed and help us making this mapping between the signals collected and the failure modes that are occurring. So the idea is to take the maintenance reports and associate them to the time series of the signals that have been collected in order to build automatically the diagnostic system that detects the different detection modes. Of course, these are separated sources of information, the maintenance reports and the signal time series, okay? So they're not already mapped one by one, so we need, or one-to-one, so we need to elaborate or build the algorithm that does this mapping. And the part of the maintenance reports, of course, it's made of free text, which has been written, filled by the operators in a very unstructured way. Okay, there are not fields that contain structurally the information in a very ordered and systematic way. So here's a little bit of a scheme of how this has been performed. So starting from the maintenance report, processing the text by natural language processing, algorithms of processing natural language, and clustering the results of these natural language processings, we are able to distinguish families, clusters that are different in the fault mode, okay, in the fault mode, and in the maintenance intervention that has been applied to take care of that fault mode. Automatically, we don't ask the expert to go to all the files of all the maintenance reports and do this discrimination of different families characterized by different fault modes and different maintenance intervention. And also, we extract the very relevant information for doing the mapping of when the fault occurred. So now we can go in the signals manipulation and elaboration with an unsupervised anomaly detection model based on artificial intelligence that looks at the prior signals prior to the date of failure that we know from the elaboration of the text, looks at the signals prior in the window prior to the failure. And so we are able to match the different types of failure modes, okay, with the signals anomalies that we have recorded prior to the different failure. This has been quite effective in providing an automatic diagnostic system for identifying multiple anomalies in the signals and matching them to the particular failure mode, so that now you know what kind of maintenance to perform. the approach, the model is applicable to all domains. We applied it to the transportation or railway transportation domain, but it's applicable to all the domains that have available knowledge in terms of input text reports and signal data. It can continuously be updated for new failure modes occurring, for new conditions arriving, okay? And it also allows the experts to go and look at what has been found and improve even the precisions and accuracy of the diagnostics that recognizes the particular failure mode. And in this case, I kind of like to call this, instead of artificial intelligence, more augmented intelligence. So making use of all the KID, knowledge, information, and data that is available, okay? The large data, the text reports, put them all together in your recipe for detecting the anomaly. Now, that's very good. And then I do the maintenance intervention, thanks to the fact that I know what is the degradation mode. But actually, it is found that for similar components, same maintenance interventions taken in different conditions at different times have different effects, okay? And this is due to the fact that other aspects enter the picture, and the effect on the performance of the components and systems is different, even if you're thinking that you're doing the same maintenance to similar components. And in fact, this is summarized somewhat here, okay? The additional effects that can be such that the treatment, the medical treatment, the maintenance treatment done on certain components, can be lubrication, balancing, replacement at different times on a certain component can have a different effect on the performance. We were looking again at some subsystem of a fleet of trains, and the difference is clearly due to different conditions, as I mentioned before, in which the train has been operated and maintained, stress condition, past maintenance intervention. So the history, the medical history of the component is such that with the same type of failure mode, same maintenance intervention, the effect can be different. This is very similar also to what happens to human beings and their medical treatment. So here is the Y, which is the key performance indicator for cluster trained of similar maintenance intervention and similar failure mode. Okay, given the maintenance performed, the effect on the key performance indicator is actually different because of the causal impact, okay, done by or given by a number of external factors like seasonal conditions, load features, the maintenance history, and so on. Typically, the performance is measured in terms of conditional average treatment effect, okay, on the performance. And here you see an example of these differences. These are 8 clusters that have been identified in the trains belonging to the fleet of trains considered, okay? And this is this conditional average treatment effect on the functionality of the component, the key performance indicator. And you see that the treatment, the same treatment, is different for the different classes, okay? There is variability. These are prediction confidence intervals, okay? And the red and the blue distinguish 2 types of artificial intelligence algorithm to try to identify the value of the effect of the treatment on the performance of the train, given also the co-founders of external conditions. Now, if we go to reliability, okay, after being in maintenance engineering, a component during its life goes through different phases from the design to the, let's say, end of life. Here it's the failure rate, let's say let's say the frequency or the probability with which a component fail in time. And as you're very well aware, this is a typical bathtub. It looks like a bathtub model, okay, where in the early times you have failures which are relatively frequent. The value of the failure probability is high because of manufacturing defects, assembling errors, certain things that are typically covered by insurance. Okay, that's why when you buy your car, you have an insurance for the first years or the first thousands of kilometers of use, because at the beginning something can happen and you need to adjust it. In this phase, okay, you want to make sure that you control this as much as possible by doing burn-in tests, okay, tests that on lots of productions, okay, that want to screen out the lots that are weak, that are defective, okay, and they are not going to sell, okay, because they would fail in usage, okay, with a relatively high probability. Then there is the useful life of the component, where the failures occur in time with the same probability, so they're intrinsically stochastic. And here you want to make sure that this reliability level is kept to proper control of extrinsic potential causes of failures. And that's where you do accelerated life tests to check the conditions of usage of the components in terms of density, in terms of temperature, humidity, and so on. Okay, and make sure that you can guarantee this level of failure probability under these conditions. And then, of course, there is throughout some aging, some degradation of the component, some wear out. And here the issue is, how do I keep this wear out and push it down through maintenance, learning from field data that I acquire from failures of similar components in their youth. So reliability testing becomes a fundamental topic for industry, for production, manufacturing industries, okay, where at the design level, you want to make sure that you have eliminated all the defects and all the defective products through accelerated life tests. During production, you do burn-in tests. And at the end, you do the detection of wear out and degradation. You go to maintenance, as we have seen before, when you're using your component. So reliability testing is an effort of acquiring the knowledge, information, and data, okay, to get some knowledge for building your reliability model and optimize these testing activities with respect to the target reliability that you want at that point, okay? And so that you optimize your decisions for your key performance indicators. Now, we have been developing a framework of accelerated life test optimization, okay, for licensing the reliability of the product that we are producing with respect to the stated conditions of use. Okay, before we send it to the field, before we send it to sale. So we start with the prior knowledge that allow us to set the parameters of our degradation and reliability model. Okay, and given this, we need to define how to set up the testing of the products that we are ready to sell. Okay, how do we test it clearly? These products might need to last for 10 years and live and operate under various conditions, and I cannot wait 10 years to know if my samples of components are robust, are reliable as I want them to be. So I need to accelerate this test. So I need to set the testing in terms of higher temperature, higher humidity, stronger and more frequent vibrations. I need to challenge my systems, okay, and components. So I simulate that on my AI model, and based on that, I'm able, through a particular mathematical framework that is able to revisit and update the values of the parameters of my model, I can finally embed my model in an optimization to give me the best expected information gain, okay, of the given setup. So I test every setup and setup, okay, of the test. I calculate the expected information gain. So it's how much I improve my reliability model by updating the parameters, okay? So that eventually I know at what temperatures, at what humidity, at what vibrations, how many samples I need to test to get a confident evaluation of the reliability of my component. This is extremely important for manufacturing and production processes in general. Now, if I go to energy saving, okay, so now I'm looking at resource efficient industry. Digital twins can really be supportive for making the right decision on how to control my energy hungry components, okay, and elements, okay, so that I keep the energy service that I'm providing, okay, with the minimum expense of the energy resource. Suppose you have a building, for example, or industrial facility, okay, and you got your BMS, okay, and of course you are collecting data, temperatures and other data from power absorption by the rotating machines, whatever it is, okay, flow of air and so on. So you have this data and you send it, okay, including external information, okay, on prediction weather, on the energy market, and all environmental and operational setting. So this is your knowledge and information data of your overall environment of operation, which is energy hungry, okay? You got data on the conditions of the elements of the building and industrial facilities. You got data from weather, energy market, environmental settings, okay? You build an artificial intelligence digital twin that absorbs, receives all this kid knowledge, information, and data, okay? And is able to send predictions and call to action, okay, in order to implement the proper actions, the proper controls on the energy machines, so that you can, in fact, obtain a reduction of the energy consumption, okay, and you implement, you actuate the changes needed to achieve this reduction. We have a couple of examples. By the way, Energy Mind, which is a product that we have developed, is actually applied and applicable because it's a platform that can be customized to different types of applications. Okay, and this is extremely important because it really enables the energy savings in different settings. How does it work? Okay, so all the data that is coming from the system and from outside the system can be manipulated by an artificial intelligence, and we call it black model, okay, through machine learning, artificial intelligence, to tell us what we should do, okay? But at the same time, we are also able to build simulators of the energy behavior of the components and systems, okay, based on technical analysis of how the systems function, okay. So we got physical models. Well, we combine both. So our knowledge, information, and data is actually on the system, is actually combining in what we call a gray model, okay. It's combining the data and it's the outcome elaboration by the artificial intelligence black model, the outcome, the results of the physics-based model, the white model. Of course, it's getting also the outside data, for example, the weather data from weather databases, okay, in real time. It elaborates all this in an optimization loop where, given the estimation and prediction done by our gray model on the energy state of the system and the stresses and pressure from outside, okay, it rewards the best state estimations and predictions, and then based on that gives warnings for operation and maintenance of the components, and more so gives actions, okay, to implement to the systems to reduce the consumption of the energy and also to improve the model itself. So you build this loop of optimization that makes it a digital twin. The development of Enermind has been performed and applied and deployed in practice in collaboration with Politecnico di Milano, so that we are sure that we are always on the edge of the best practices for the modeling parts, okay? And here's an example on an Italian health center, okay, that we applied Enermind, okay, where we had the actuators that would allow us to turn off the pumps and the boiler during intervals in which some of the rooms of the health centers, some of the operation rooms and waiting rooms and diagnostic rooms of the health center were not occupied. By intelligent optimization based on artificial intelligence, machine learning, we were able to operate the different machines with the preconditioning, again, coordinated by machine learning. And you see here the savings obtained on the energy consumption of the boiler and the pump, okay, in weekdays and weekend days, for an overall interesting total saving of 32% on the operation of the main components, main energy components of the health center. So 32%, also given the more and more challenging energy market and energy price, is a significant gain that we were able to achieve. Another application quite different is on the heat, ventilation, and air conditioning system of naval and civil facilities within the naval industry. And again, here we had a physical model of the system. We had data we had data collected by the sensors, okay, and we were able to combine them, okay, elaborate the data with black models, elaborate the physical model to get a result from their running, and put them together in a gray box model, okay, which actually, again, identify policy of usage of the energy components in the system for a 30% decrease. And actually, this was eventually applied to ship design, okay, ship design, so that through the evaluation of the energy consumption, we were able to influence the ship design through some of the insights that were achieved from this work. So these were just some use cases related to industries that not necessarily relate to your specific industries. We've seen transportation on rail, we have seen health centers, we've seen the naval industry, but you can do your homework exercise of transposing within your industry the idea of combining all that is known on a component in terms of physics models, in terms of texts, because of the reports of inspection and maintenance, because of data collected by sensors, and having a properly set up artificial intelligence model that tells you the state of your components and system, diagnoses if something is going wrong, detects and diagnoses it, and this suggests how to operate the system, how to make it more reliable, how to optimize the testing of the products, or how to reduce energy consumption in buildings and other usage of industrial facilities. Now, artificial intelligence is clearly at the center of what is more and more pushed as Industry 5.0, where all that we're saying, all that we've said and presented up to now, is becoming more and more human-centric, okay? So the efforts of advancing artificial intelligence and digital to be able to use all the knowledge information that are available for our purposes of reliable and resource-efficient industry is as at the center the human being as an operator and as a civil person, okay? So human-centric technologies to enable competitiveness, but with the solutions that are sustainable and resilient to disturbances that could account for very different reasons. And that's why you see more and more the rise in artificial intelligence of so-called foundational models. For example, the large language models built in ChatGPT, which are generalized, allow anybody to apply, at least the ones that are free, to apply artificial intelligence for their purposes, okay? You see the proliferation of these pre-trained models, not on the data and on the knowledge information of your industry, but any data that can be found related to your problem, to your objective, okay, that can be found in literature and in other ways, okay, to train them and use them. And that's what we do when we do and use ChatGPT for our personal purposes also, okay? Of course, this is quite, and computational energy and economic resources, the costs that are associated to the data centers and to the training of these, pre-training of these large language models, these foundational models. And of course, for industry, because one thing is if you're marketing products and if you are choosing music and if you want to know who is somebody, okay? But in industry, okay, tailoring and customization is quite important, and the foundational models sometimes are so general that you don't find a solution for your specific setting. So deep customization becomes very difficult for these very large foundational models. However, this really hype for these foundational models is seeing also a strong dominance of the big companies that have the economic power to be able to actually develop these solutions of this size and of this capability of generalization. So this makes it difficult eventually to differentiate AI solutions that are built through large foundational models because they are all coming from the same sources of general information. And so it is also difficult to give the right value, okay, to the AI solution that is proposed. because it needs to fit your particular context and your particular objective. Okay. Of course, the fact of sharing the knowledge at large in these foundational models gives certainly benefits, okay, because it accelerated the technical developments. But, and I tell you, in a sense, from an academic point of view, nowadays it's kind of difficult. There's so many papers that are coming out, so many informations coming out from the next model, the new model with a better accuracy, that you are having a hard time to distinguish really what is good, what is original, what is an advancement, and what is relevant for my application and my particular needs. Okay, so there are a number of challenges to actually bring artificial intelligence. The opportunities, I hope you have appreciated them through the use cases that I have proposed to you. There are certainly a lot of great opportunities, but we must be aware, of course, of the accuracy, of the challenges. In the end, the big challenge is making sure that the AI algorithm, which is a new element in your system that you're using, for example, to decide your maintenance or to decide how to run your energy components, okay? Make sure that you can trust it, okay? Make sure that you can trust its indication. Make sure that you have a way to understand how it arrives at this conclusion, okay? Because then you can trust it. So really, you need to guarantee that the knowledge, information, and data that you have put in the algorithm to train it and to build it, it's validated, okay? You make sure that your algorithm is accurate with respect to what you want in outcome. You must have confidence on your outcome. It must be consistent on the physical knowledge that is available, okay? If you know something physically should go that way, you expect that the artificial intelligence output go that way, okay? And you want to explain why the artificial intelligence told you that it goes that way. So if I open the challenges briefly one by one, knowledge and information, you have it. How do I validate it? For example, one very difficult problem is a sensor failure. We are now collaborating with a gas distribution system operator who has issues in the mountain when the mountain sides could fail and have let's say an avalanche or things like this, and the sensors that are implemented to understand if the flow of the gas is okay and the pipeline is okay, they might fail. They might fail. Okay, so sensor failure is a big issue. Sensor failure is a big issue. Now, there are ways, and we're working on ways on how to validate the signals that are arriving that you want to use to build your artificial intelligence, and even reconstruct how the signal should be. Okay, so reconstruct the clean signal, the correct signal. There are artificial intelligence algorithms that allow to build the proper signal that you can then use for your artificial intelligence model construction. Now, accuracy, of course, is very important. Suppose that you want to classify the different degradation modes of your train subsystem. You want your artificial intelligence box, your artificial intelligence component, to be correct, not to misclassify degradation modes and then you do a maintenance which is the wrong maintenance. Now, typically, the issue here is what we mentioned before, that the training for the classification, unfortunately, does not have the labeling. You measure the signals, X1, X2, but you don't know what do they correspond to, what degradation mode they correspond to, okay? So you got that the labels are not available to tell you that this is green, this is red, and this is blue. And also, typically, since we build components to operate properly and not to fail, most of the signals that you are using to train, you're collecting and you're using to train and build your model are for good class, are for conditions of good operation, not to discriminate anomalies. So they are in balance. The majority of the sample signals you have relate to the good operation class. So your classifier, your diagnostic automatic tool is much more accurate in diagnosing that everything is going well, but there's a hard time recognizing the anomalies. Again, there are ways. We saw an example where we use natural language processing of maintenance records to label and match, do the mapping between the signals measured and the degradation modes. Okay, there are other methods based on generative AI, generative artificial intelligence, to create samples and examples from the anomaly classes. So that now the training is just, okay, is balanced. And this is very important, okay? And you can do that so that you can use it properly. You must have confidence, okay? If you tell me that my component will fail in 57 hours, 25 minutes, 18 seconds, I don't believe it. It's too precise, okay? It's too precise. There are so many sources of uncertainties on the sensors measurements, the stochasticity of the degradation itself, and the future stresses from outside. The model itself is approximate, okay? So how can I believe such a precise evaluation, okay? So there are ways to understand and estimate the uncertainty associated to your prediction in this case, okay? And if you tell me that more or less, okay, you should expect failure in between 55 and 60 hours with probability 90%, that's a much more informed indication that will help me take the decision of should I stop now, or can I take still this day of production and then stop, or even 2 days of production and then stop. Okay, I want prediction, confidence. Okay, then consistency, as I mentioned before. If I have some laws of physics that I know that pressure and temperature must both go up, if I have empirical expertise that shows me how the current and the vibration should be related, I want my model to reflect this. Otherwise, I don't believe it. I believe in physics, okay? And that's why you see all these efforts in developing solutions of physics-informed artificial neural networks, where you bring in the artificial intelligence model, you bring in both the data and what you know of physics. And your artificial intelligence algorithm accounts for both what it learns from data and what it knows from physics, with very good results, okay? And finally, I get all this in, and I have my box, and it tells me the outcome. The component is damaged. I want to understand what is the reason why it's giving me this outcome, okay? So explainability. There are ways to open windows in the black box, to look inside at how the data are related between input and output, and why for certain input a certain output comes out. And this is extremely fundamental, particularly for safety critical or critical applications in particular. And I think I can stop here. I think this picture is a little bit the challenges of what expect to us for an actual application on all kinds of industries. I hope that I was able to transfer to you the opportunities that come from artificial intelligence and some points of attention. If we want to go there, okay, let's look at what we have in terms of knowledge, information, and data, and what we get, not only in terms of numerical outcome or decision outcome, but also on how accurate it is, how confident we are, is it consistent with physics, and can we have some explanation for that?
Thank you, Professor, for your great masterclass. I'm sure that all the participating SMEs will take away a real value from today's session. Unfortunately, Sidesh had to leave, so on behalf of Astintal, I would like to thank you all for joining today's workshop. And that's it. Wishing you all a great day. Hope to see you soon.
Thank you very much again. Thank
Goodbye.
you. Bye-bye.